Hi everyone. Today I'm going to show you guys two ways to use calculus to calculate the surface area of the sphere. Okay, we're going to think two different ways to do that. So I'm going to show you guys this the first way. The first way, we're going to add these rings in here. Okay, so it's going to be first this ring. We're just going to calculate half the sphere and then multiply by 2 to get the total surface area of the sphere. So we're going to calculate this ring plus this one, plus this one, plus this one. Of course, all the way up there. Of course, there's going to be an infinite amount of rings, right? And they're going to be infinitely close to each other. So we're going to add this one, plus this one, plus this one, plus all these rings in here, and we're going to multiply by this length in here. Of course, we have to relate, okay? We got to relate this length in here of the sphere with y. Well, in this case, we're going to use theta, okay? From experience, I just know that it works. So I'm going to show you guys this stuff in here. I don't know why this is not showing. Okay, it's showing now. All right, so just want to make sure. Okay, so how do we calculate those rings, right? Well, it's going to be 2 pi. Well, what's the circumference of a circle? Because each one of those rings is a circle. So it's 2 pi r, and for each circle, r is going to be the value of x in here, okay? Now, I know from experience that if you try to relate x to y, it's just not going to work. So we're going to integrate this time with respect to theta. So what's going to happen is that we're going to get the first radius here from the first vector, and then we're going to add another vector and all the way up here, okay? That's how we're going to find the radiuses of, well, the radii of all the circles, and we're going to multiply by this length right here, and this length we're also going to relate that to theta, okay? So here we go. Since we're going to have to be working with theta, we got x equals r cosine of theta, and y equals r sine of theta, and dx d theta equals minus r sine of theta, dy d theta equals r cosine of theta. Great. So it's going to be the integral, okay, from the 0 degree here all the way to pi divided by 2, because pi divided by 2 is 90 degrees, right? So it's going to be from 0 all the way to pi divided by 2 of what? Of 2 pi. Well, 2 pi is a constant, so I'm just going to leave it out of the integral. 2 pi r. R is going to be the value of x, and the value of x is this thing right here, r cosine of theta. So you have r cosine of theta. Okay, but we are integrating with respect to, well, yeah, it's going to be 2 pi r, which is for each one of the rings is r is x. So it's going to be this value right here, okay? And how long are we going to do that for? Well, we're going to do this for all this length in here. So for you to have this length, you got to calculate it, right? Well, we know that this is just the length of it's 1/4 of the circle right here. So we know that it's, we know what it is. It's like, that's going to be pi, well, it's going to be pi divided by 2, but we're not going to worry about that. Actually, what we're going to do is we're going to have to calculate this length in here with respect to theta. How do we do that? When we use that formula that relates that finds the length, okay? It finds the length of a curve on a plane using calculus. So it's going to be the square root of this squared, which is going to be r squared sine squared. I'm just going to put this to make it smaller. Sine squared of theta plus, yeah, that was dx d theta squared. And the next one is going to be dy d theta squared, which is just going to be r squared cosine squared of theta. R squared cosine squared of theta. Okay? And now, well, you see this thing right here, this stuff in here is just going to become 1. Why? Because let's factor out, well, yeah, it's just going to become r. Why? Because you're going to factor out the r squared. So you're going to be left with sine squared of theta plus cosine squared of theta. Sine squared of theta plus cosine squared of theta is just 1. Okay? So you have r squared inside the square root, and this equals r. So we're just going to replace this stuff in here with 2 pi. You have an r here, and this is also r, so it's going to be 2 pi r squared, the integral from 0 to pi divided by 2 of what? Of the only thing that's left, which is cosine of theta. Oh yeah, the integral here is going to be with respect to d theta. So you're going to have cosine of theta d theta. This is going to be equal to 2 pi r squared. And you have this, the integral, right? Yeah, the integral from 0 to pi divided by 2 cosine of theta. Well, the integral of this is just sine of theta. So you're going to multiply this by sine of theta. Yeah, theta right here. And, well, you see this whole thing in here. This theta became quite a mess. Sine of theta. Okay, and this is going to go from 0 all the way to pi divided by 2. What is the sine of 0? The sine of 0 is 0, and the sine of pi divided by 2 is 1. So this whole thing here just becomes 1, okay? And you have 2 pi r squared. Now, this is just for half of the circle, half of the sphere. So you have to multiply this by 2, and you're going to have 4 pi r squared. That is the formula of the surface area of a sphere. Okay, so we already found this, 4 pi r squared. This is one way of thinking. This is one reasoning, right? You find each one of those. Let me show you again. You find each one of these rings in here, and you get its circumference plus the circumference of the next one plus the circumference of the next one plus the circumference of the next one, which is going to be this one, plus this one, plus this one. And you do this along this length in here, right? This length in here of the sphere. That's what you do. That's what we just did. Now, I'm going to show you another way of thinking about this stuff. Okay, so we already have the surface areas, 4 pi r squared, where r is the radius of the sphere. Okay, that's wonderful. Now, we're going to think about this in a different way. How to solve this problem in another manner, okay? In here, you can see that you have this piece and this piece. This piece in here came from this sphere. This piece in here came from this sphere. Okay, I just put more isoparms in here, horizontal and vertical isoparms. So you can see, why did I do this? Because you can see that this sphere has a lot more isoparms than this one. Okay, so it's like in this sphere in here, these little pieces are just growing smaller and smaller and smaller and smaller, and that's what's going to happen in the integration. That's what we're going to do now. These things in here, which are these pieces, are going to be extremely small. And as they get small, I'm going to show you guys this stuff in here. You can see that this one came from this sphere, okay? This one right here came from this sphere. You can see that it's a lot more curved. It doesn't look like a plane as this one that came from this sphere. So as these pieces in here, these faces in here become very small, they become more and more like a a rectangle, okay, a plane, a rectangle on a plane. So I'm just gonna show you guys this stuff. Can you see that this one in here is a lot more curved than this one? Look, you can see the curvature in there. Okay. All right. Now, what am I gonna do? What I'm gonna do, the way of thinking about this now, I'm just going to, let me think here. I'm gonna show you guys something. Pretend that you got a vector that's coming out of the center of the sphere, okay? And this vector can sweep two angles. Now, the theta angle is the one that remains on the same. It remains on the same parallel, the same horizontal isoparm. So when you get out of this spot right here, when you get out of this spot and you come here, you're just sweeping an angle theta. Okay, like when you get out of the, for example, this spot right here and you come here, you're just sweeping an angle theta. Now theta is going to sweep 2 pi, right? Because it's going to sweep all around in here. Now you have also another angle, which is phi, which sweeps the vertical isoparm in here. So it goes all the way from, let's put it this way in here, it goes from pi divided by 2 all the way to 0 to minus pi divided by 2. All right, that's what's going to happen. And the plan in here is that you're going to have, at the center of the sphere here, you're going to get out of this spot right here, and you're going to come down. Okay, so there's going to be a vector that comes out of this and comes all the way in here. Now it sweeps from in the phi angle, it sweeps from minus pi divided by 2 all the way to 0, all the way to pi divided by 2 over here. And then it sweeps an angle of 2 pi in theta. Okay, so what's going to happen, I'm going to show you guys here a little animation that makes it easy for you to understand what's going on. Okay, so in here you have, of course it's invisible. I didn't actually draw the vector here, but the vector is going to come here, right? And it's going to go all the way down here, and this is going to be at the position phi minus pi divided by 2. When it sweeps all the way here, it's going to be at phi equals 0. And then it'll come here, it's going to keep sweeping and sweeping and sweeping all the way to pi divided by 2. Now you have an arc in here, and this arc is going to be swept 360 degrees in the theta direction. So this is what's going to happen. Okay, that was a little bit fast. So you see that this is what's happening. It's just sweeping this stuff. Look, informing the sphere. Okay. Of course, you got to increase the sections here. When you sweep the stuff, you got to increase the sections. So each one of these faces is equal to this face right here. All right. So that's what we're gonna do now. How are we gonna do that? I'm gonna erase this thing, all these things in here. Okay. Now you see what I'm gonna do is that the angle, okay? We're gonna start with a vector here, and at this point, phi, okay, now this is not theta anymore, this is phi. Phi here is gonna be minus pi divided by 2, and then when it gets here, it's pi, it's 0, and when it gets over here, it's pi divided by 2. Now there's something else that I gotta show you because this is a very complicated way of thinking. You see here what's happening? I'm gonna put the isoparms in here again. Let's show, how do you calculate, what you're gonna do is to calculate the area. As these things in here, these faces become extremely small, they're going to approach a rectangular on a plane, a rectangle on a plane. Okay, now what do you have to do? What you got to do is that if you're in here, in this point right here, okay, you're in this point right here, and you want to calculate the area of this face in here. Let me think here. How am I going to do this? I think it's surface point. No, it's not surface point. Surface patch. Yeah, surface patch. So you have this thing right here. Let me just assign my material. There you go. Now you want to calculate the area of this thing. Okay. How do you do that if this approaches a rectangle on a plane? It's this length right here times this length right here. Okay, it's the area of a rectangle. Great. How do you do that? Well, you see, let me just, okay, that doesn't really matter. From the center of the sphere, you're going to have a vector that's going to come, for example, from here all the way down here. What's going to be this length in here? It's going to be r times the angle swept, okay? Because this length right here is going to be an arc or arch. I think it's an arc. I think it's pronounced arc, okay? So you're going to have an arc, and the length of this arc right here, the length of this stuff is just going to be r times the angle swept, which is phi, okay, times this thing right here. Now this thing is going to be r times the angle swept, which is theta. But this length depends on the angle phi, because you see, when the vector is coming from this to this one, to this one, to this one, it's just sweeping an angle in theta. It's not messing with phi. So it's going to depend, okay, on the cosine of phi. How does that work? Let's look at the equator here. You can see that this isoparm, I'm just going to put it in isoparms again. When you're doing here, okay, from this point to this point, it's long, right? And as we go here, let's think about this isoparm. From this point right here to this point in here, it's smaller. You can see that as it gets closer to the poles, right? Now we're here. Let me just try to get very close. Now you're in this isoparm. So from here to here, it's still going to be the same theta angle that you're sweeping, except that the length in here is just going to be small. Okay, so it depends on the angle that phi does with the surface. So how do we do this? Well, you see, it's going to be the integral, right, of all those little rectangles. Now, yeah, I'm not showing you guys the rectangles, huh? What I'm doing. So it's going to be the integral of all those little rectangles, okay? When you have, I'm just going to pretend that this is a sphere, okay? So let me just do this here. This is going to be very crude. So let's just pretend that you have something here. And you got another part in here. Okay. And now you have this, and you have this. All right. So from here to here, it's just going to be what? You want the integral of all these little pieces, right? So it's just going to be the integral. We're going to have two integrals here. From this part to this part, what's that? It's r times phi, okay? So it's going to be r times the angle phi. Actually, phi is going to be so small that's not going to be phi, it's going to be d phi. Because d is just, you got to remember that these rectangles are infinitely small. So it's just going to be d phi, okay? And now you have to worry about this length in here. This length in here is going to be r, because you have to multiply, right? So it's going to be r d theta. Now, this thing in here is going to depend on the angle phi, on the cosine of the angle phi. So when we're talking about the poles here, phi is divided by 2, right? The angle that the phi is doing. Let's just say that you have a vector in here, okay? So the angle that it does with the horizontal, with the floor right here, is pi divided by 2. What's the cosine of pi divided by 2? It's 0. So how much is it going to be swept in this direction right here? Nothing. You're not going to sweep anything in here because you're at the pole, okay? Now, as you come out of the pole, things just start getting a little bit larger and larger and larger and larger until it gets to the largest at this point, and then they start becoming smaller and smaller and smaller and smaller and smaller and smaller until you get to 0 here again. So what is this length in here again? The length in here again is going to be r times d theta times the cosine of phi. Okay, now you have d theta and you have d phi, so you have two integrals here. I'm going to take care of the theta first. Okay, the theta is going from 0 to 2 pi. Okay, because it's going to sweep all around in here. It's going to sweep all around in here. Okay, now phi is just going to go from minus pi divided by 2 to pi divided by 2, right? It's going to sweep from here, minus pi divided by 2, and it's going to keep going, keep going, keep going, keep going, until it gets to about here of pi divided by 2. Okay, so we have this stuff. I'm going to integrate, so theta first. Why do you have theta? You just have in here, okay? There's something else that I want to do. You see this r and this r, that's r squared. That's it's multiplying everything, so I'm just going to get this out of the equation. It's just going to be out of the integral. It's going to be r squared, and then you have the integral from minus pi divided by 2 to pi divided by 2 times the integral from 0 to 2 pi of what? D theta, and then you have cosine of phi d phi. Okay, so what's the integral of theta? D theta is just going to be theta. Okay, now theta is going to go from 2 pi to 0. When it's 0, it's going to zero everything out, so don't worry about that. So this d theta here is just going to become 2 pi. So you have 2 pi r squared, and now you're just going to integrate minus pi divided by 2 to pi divided by 2 of what? Cosine of phi d phi. What's the integral of cosine of phi? It's going to be sine of phi. So it's sine. As a matter of fact, I'm already integrating here. Sine, yeah, I'm gonna erase this thing because I'm already integrating. So it's gonna be sine of phi, okay, and this you're gonna plug in from minus pi divided by 2 all the way to pi divided by 2. Now 2 pi r squared, and then what do you have in here? You gotta plug in the pi divided by 2 in here in this angle. What is the sine of pi divided by 2 is 1. Okay, minus, and now you gotta open this parenthesis here. What's the sine of minus pi divided by 2? That's minus 1. So you put a minus 1 in here. Okay, so 1 minus minus 1, that's 2. 2 times 2, that's 4. 4 pi r squared. And there you go. You have two different ways of finding the surface area of the sphere.